recorded today. All right, so yesterday, this is right where we ended up. We're talking specifically about how to deal with resistors in series, but the goal had been from the very beginning to come up with a relationship for how to deal with resistors in series so that we can produce from that an equivalent circuit. I want to keep reminding us, this idea of equivalence is that this circuit serves the same purpose according to the electric potential as the circuit before, meaning the battery doesn't know any different. It's going to produce current in the same fashion that it did before. It doesn't know what's been connected between its terminals. All it does is generate current. The equivalent resistance is treated as the same as the system of resistors. So I think it seems appropriate today that we take a look at circuits in parallel. And then once we've done that, we're going to take a look at some more complicated circuits. Get to the good stuff. So parallel resistances, just like we had before, aren't much different than what we had. The major difference here is that there's now a break in the current. And this also allows us to start talking about another law in Kirchhoff's set of rules. We've been dealing with the loop rule to this point, but now we have something we have to add to that called the junction rule. And Kirchhoff's rules are, again, they are just extensions of conservation of energy and conservation of charge. The loop rule is a conservation of energy rule, but the junction rule is a conservation of charge rule. It governs how the charges actually behave in a circuit like this. So if we label this one as R1 and this one as R2, if we want to use Kirchhoff's rules, one of the things that we have to start understanding is that for Kirchhoff's rules to successfully function, you need to determine a loop that encompasses all potential branches of your circuit. Or better yet, you need to use the number of loops necessary so that every circuit element is incorporated. This circuit has 3 potential loops. There's this loop that we could use to discuss this circuit. There's this loop that we could use to discuss this circuit. And then there's this loop we could use to discuss this circuit. 3 potential loops. You don't necessarily need to use all 3 loops, but you do need to use enough loops so that every circuit element is represented somewhere in one of your Kirchhoff equations. So although there are 3 loops here, I think we only need to do 2 of them. Now, I do want to point out a couple of important details here, and this is going to become more and more difficult as the circuits become more complicated. We have a voltage here, which I'll call V1, and a voltage here I'll call V2. I indicated before that when we use Kirchhoff's rules, batteries tend to add voltage and circuit elements take voltage away. That's not entirely accurate. And although I don't want to get into the super details of this, it has something to do with what we saw last time when we started dealing with whether we're in series or parallel with capacitors. With capacitors, if you remember, if you're going from the negative side to the positive side, then you're increasing the potential. If you're going from the positive side to the negative side, you're decreasing potential. Resistors are a little different. If you're going with the current, then you're decreasing potential. If you're going against the current, then you are increasing your potential. I'll say that again. When drawing these loops, I've made an assumption of a direction, right? You'll notice that every one of my loops has an arrow in it. That's the direction of what I feel is the likely direction of current. However, if the current is going the opposite direction of my arrow, then I add the voltage from that circuit element. If the current's going with the direction of my arrow, then I subtract the voltage across that circuit element. Now, that's not going to come into play for a long while for us, but we need to be cognizant that we need to be paying attention that these loops are drawn in such a way that we understand whether we add our circuit element voltage or subtract our circuit element voltage. This will probably never come up on the exam because they just don't have complicated circuits that are trying to get you to figure out what direction a current is, usually nothing more complicated than 2 or 3 resistors max. But I want you to be smarter. So we have to kind of decide which of these loops we're going to use so that we don't have to run into this problem at all. We're going to ignore the green loop. The green loop is the only one that would have caused us to have any problem dealing with direction. If I use just the yellow loop and the blue loop, I've drawn them specifically in a way to ensure that the voltage drops from our resistors are actually negative voltages. Because if we just look at this picture, we know that that has to be the direction of the currents. So we'll get into something a little more complicated later in the semester, but not now. So I'm going to do the yellow current first. If we assume the battery has voltage V, then I'm going to have V minus V2 equals 0. That's the yellow one. And if I'm going to do the blue one, I'm going to have V minus V1. That equals 0. Again, some of the voltage drops has to equal 0. Now, ultimately, I could stop right there. This kind of tells me that V and V2 are equal and V and V1 are equal. That's not a surprise. Ultimately, if I look at this circuit, it might not look like it, but it does have the appearance that R1 is connected directly to the terminals of my battery, and R2 is connected directly to the terminals of my battery. So they're each receiving the voltage of the battery. The problem is that that doesn't tell us very much when it comes to what's actually happening. What's our equivalent resistance? To figure out our equivalent resistance, we have to see how that actually impacts the battery. And to do that, we might need to deal with the fact that there's currents passing through here. Now, this brings us to a new rule called the Junction Rule. And the Junction Rule deals anytime there's a split in the current. And it states quite simply, current in has to equal current out. That's it. Current in has to equal current out. So when I look at this junction, there is a certain amount of current going into the junction. I don't know how much current that is. I'm going to label that, I don't know, I for the battery. Now, exiting that junction, there's this current that goes through resistor 1, so I'll call that I1. And there's this current that goes through resistor 2, I'll call that I2. If I want to use Kirchhoff's law correctly, then I for the battery has to equal I1 plus I2. That's how the junction rule works. So I battery equals I1 plus I2. So I want to kind of combine all this, try and figure out what my equivalent resistance is. When I analyze my circuit and come up with some expression for the equivalent resistance. So I'm going to do what I've been talking about for a while. We tend to use Kirchhoff's laws in conjunction with other rules, and I'm going to use this rule. Ohm's Law. Why we're dealing with resistors. So I'm going to say that V minus I2R2 equals 0. And V minus I1R1 equals 0. Now, if I do that, I could probably come up with something for I1 and I2 in terms of the resistance. So that's what I'll do next. I'm going to say that I2 is equal to V over R2, right from Kirchhoff's laws. And I1 equals V over R1, right off of Kirchhoff's law. I can plug those in. So I get the current from the battery has to equal V over R1 plus V over R2. Now, if I want to find the equivalent resistance, I'm going to apply Ohm's law to the battery. If I apply Ohm's law to the battery, then I'm going to say that V over the equivalent resistance has to equal I for the battery. This is what the battery thinks is connected. So the battery is producing current based on its own potential and the equivalent resistance that it believes is attached to its terminals. And this has to equal V over R1 plus V over R2. This produces no surprise, right? That ultimately all this tells us is that the equivalent resistance for resistors in parallel is equal to the sum of the inverses inverted. So these first two circuits were just to show us how to use Kirchhoff's laws and Ohm's law to produce two related pieces of information. That for a series circuit, the equivalent resistance is equal to the sum of the individual resistors. And for a parallel circuit, 1 over the equivalent resistance is equal to the sum of 1 over the individual resistors. Capacitance is the opposite. And in addition to that, we have Kirchhoff's laws, which says that the sum of the voltage drops in any circuit is equal to 0, and current in has to equal current out for any junction. Lastly, voltage equals current times resistance, but better is current equals voltage divided by resistance. There, the big sum. That's, in a nutshell, what you have to know about resistor circuits. There's one thing missing, and it's minor, but you know, I say minor, but it's like what the whole point of a circuit is, and that's to be able to distribute energy. So when we were dealing with capacitive circuits, we're always trying to figure out how much energy was stored in the capacitors. Resistors don't store energy. Resistors consume energy. So of course, after all of this, it comes right down to resistors are about dissipating power. And the dissipation of power is the combination of voltage and current. The power of a circuit is the product of voltage and current. Combine that with Ohm's law, and you get various ways that you can calculate the power dissipated by a circuit or circuit element. All right, so this is the overview from last year. All of you guys who had circuits last year, this shouldn't be a surprise. We had resistor circuits last year. This is not the interesting stuff, but we probably should at least once take a moment and do a stepwise reduction of a circuit so that you can see it done. So let's do a straightforward stepwise reduction of a circuit. How do I want to do it this? I want to do this one. This one's, say 4 ohms here. Let's make this 6 ohms and 6 ohms, 3 ohms, and 24 volts. There we go. Now, just quick show of hands. Who remembers the stuff from last year? That's a lot of you. Good, good, good. So if you've never done this before, then we're going to step through this one as our practice. But if you've done this before, you guys, try it. Go ahead, run away with it. You guys know what you're doing. So for you guys who don't remember how to do this and need a bit of a refresher, stepwise reduction for resistors is exactly the same as stepwise reduction for capacitors. So we've kind of done this already this year. The difference is that with capacitors, we had to use the definition of capacitance, C equals Q over V. For these circuits, we're going to use Ohm's law, V equals IR. But ultimately, your job generally is to figure out the voltage, current, and power for one of the resistors in the circuit. These circuits can be analyzed by using stepwise reduction, which is going to be easier than using Kirchhoff's laws. And stepwise reduction is the reduction of a circuit, system by system, using the rules for series and parallel until you reach a single resistance as your equivalence. So what that means is I'm going to look for examples of series or parallel. And I can only reduce a section of the circuit that is strictly series or parallel. So the first thing I'm going to do is I'm going to reduce this part of the circuit. It's strictly series and allows me to make a reduction by using the rules for series. So I tend to not draw the voltage supply every time I reduce the circuit. I just draw the resistance portion. And for you guys who are new to this, I write in the parts that we know and try and build a roadmap for how I'm going to reduce my circuit. I have an unknown I'll have to figure out there. But when I do, I notice that I have an explicit parallel element that I can also reduce. So I'm building a roadmap for how I'm going to reduce my circuit, one section of the circuit at a time, recognizing that these are in parallel and I can get an equivalence for them. And then I should end with a single equivalent resistance where I will apply the 24 volts from the battery. So going back to the beginning, I'm going to use my rules for series to combine the two 6-ohm resistors and recognize that I have a 12-ohm resistance there. I know it's been a while, but I did say that the symbol for resistance is the ohm, and we use a little horseshoe for it, but it was kind of a footnote at the end of last week. Now, I have a 4 and a 12 that are in parallel, so I've got to use my fancy math to figure out their equivalency. Add 1/4 to 1/12, get common denominators. But there's probably one of you who's going to say that that's 2 and a 16th. That would be wrong. Common denominators makes this 3/12. And I'll get 4/12. That is not the answer. That's the inverse of the answer. So the actual answer is 3 ohms. All right. And now 3 and 3 is going to give me 6 ohms. 6 ohms is my equivalent resistance. This is my equivalent circuit. Now we have reduced our circuit down to an equivalent circuit. You guys who did not do this last year, this is step 1. This is half of the work. So for you guys who this is new, reducing the circuit is probably the easier part, but requires only the use of your rules for series and parallel. Are there any questions about reducing the circuit? All right, you guys who are ahead of me, I assume that you've already started the process of working backwards. That's what we're going to do next. We're going to work backwards. And here's where we're going to use the rules of Kirchhoff to kind of step this backwards. The first thing we need is the current. And we'll use Ohm's law to figure that out. 24 divided by 6 gives me 4 amps of current. Once I have figured out voltage and current, I can step backwards and apply the information I have to my previous circuit. When making this application, you have to remember that in series, the current must be the same since there's no junction. That's Kirchhoff's second rule. So if I step backwards and I'm going back to a series circuit, I'm going to apply the current to each element that is in series. Because there's no breaks in the circuit, each element must have the same current. Once I've done that, I ignore the simpler circuit and I focus on my new circuit, using Ohm's law again to figure out the voltage for each of the elements in the new circuit. In this case, 12 volts and 12 volts. V equals IR. Now, there was a 24-volt voltage drop. Kirchhoff's law states that I still have to have 24 volts of voltage drop. You'll notice 12 volts across each adds up to be 24. Meaning in every step, you should be able to check your work. Getting circuits wrong is 100% on you because there's so many interdependent ways that you can check your work. But also, be cognizant of when you have finished a resistor that appears in the original circuit. This is 12 volts. This is 4 amps. Especially on an exam, if you only needed information about that resistor, do not do the rest of it. There's no need. But we're going to finish. So in order to finish, I got to take this resistor and step it backwards. When I'm going from a single resistance to a resistor that is in parallel, then Kirchhoff's rule says the voltage drops across each leg of a parallel circuit has to be the same because of the loop rules. That means I apply my 12 volts here, my 12 volts here. So when I go back to a set that's in parallel, you apply the voltage to each side of the parallel elements. Again, Ohm's law to figure out the individual currents. 1 amp, 3 amps. You should be able to note that there were 4 amps there before. By Kirchhoff's second rule, current in has to equal current out. If there was 4 amps traveling towards this junction, there needs to be 4 amps traveling out of this junction, and there is. 3 goes to one side, 1 goes to the other. But that finishes off this resistor, leaving just these two. And I'm going to take the current and apply it to each of them. Since they're in series, they must have the same current. And now Ohm's law, once again, 6 volts, 6 volts. And it looks to me like we have successfully solved our circuit. Questions? All right, that is stepwise reduction of a circuit. It's not particularly interesting, but it's what we're going to have to do on our circuits. So before I move on from this, are there any questions about stepwise reduction? I left something out. It's super minor, but let me make sure that we have no questions. All right. There are 2 super common misconceptions. And if you make these mistakes after I tell you about them, I'm going to laugh at you. There's bound to be somebody in the room who wants to go through and add up all the voltage and tell me that if I add up all the voltage, it's more than 24. Sure is. It's 36. You can't add up all the voltage and see if it equals the voltage that was there before. That's not a rule. That was never a rule. However, what you could do, if you want to add something up, is you could compute the power at every resistor. Take a moment and compute the power at every individual resistor, please. It's not hard. Let's see. I'll do 1. 3 times 12 is 36 watts. You do the rest. Now, I assume you guys did this okay. 36 and 48. 84 plus 6, 90 plus 6, 96. This circuit dissipates 96 watts of energy. If these were bulbs, the brightest bulb would be this one. The dimmest bulb would be these two. All from their power. So again, if they're bulbs, we would judge them by their brightness. Their brightness would be their power dissipation. It shouldn't be lost on you that 4 times 24 is 96 watts. Your equivalent circuit must dissipate the same amount of energy as your original circuit. Not the same voltage, same amount of energy. That has to be true. So if you add up the individual power, you'll get the same power as a whole circuit. On the other hand, if you choose any loop through the circuit, the sum of the voltage drop should be equal to 0. And they are. 12 volts plus 12 volts equals our 24. If I choose maybe this route, get 12 volts plus 6 volts plus 6 volts, 24 again. So any of our Kirchhoff's rules should be tested and validated here. On the other hand, Kirchhoff's rule should fit here too. Since the current is clearly going downwards through both of these, based on the direction of my battery, I have an increase in voltage on the left side of 12 volts and then 2 decreases of voltage of 6 volt each. The sum in that circle equals 0. Now, I would not have spent all of this time validating this circuit if I didn't think you would have to do this on the exam. This is more akin to what you will have to do. Being able to not just solve your circuit, but apply Kirchhoff's rules to your circuit. All right. Be honest. Who needs practice on this? Okay. I'll create a little bit of practice. I am not going to require the whole room practices. I know that if once you get this, it's like riding a bike and you've gotten it. So I will create some practice. I'm not going to do a whole lot of practice in class. How about Thursday, though? After I've put a little practice on Canvas, you've had a chance to look at it. I'm thinking Thursday I could just make sure you guys are good at this, right? You guys follow that? That's not me. That's not, no subtext. Pop quiz, first 10 minutes of class. I'm going to have a circuit, no more complicated than that. You're going to have to be able to show that you can reduce it and then apply the rules of series and parallel to go back through the circuit and find voltage and current for each element. All right? Any questions about that? Uh-oh, a visitor appears in Matt's room. It could be anybody. It's just legs. Maybe he's being challenged to a duel. We don't really know. It could be anything happening. Anything. How'd that go, Matt?
Oh, it was just my dad asking what I wanted for lunch.
What are you getting for lunch?
Probably barbecue.
I want some barbecue for lunch. From where?
From Willie Jules. It's like right down the street.
I'm going to have a bowl of ramen. Yum. I'm having emergency lunch today because that's all I had in my classroom. I forgot to grab something. But I would like some barbecue. Anybody going downstairs to the potato bar today? We listen to the lunch menu every day, second period, just to see if they're going to ever switch it up. Last week, we finally got it switched up. It was not the potato bar one of the days. It was the Fiesta bar. We were so excited. What's that? It's a Fiesta bar every Friday? So is it a true Fiesta? Like when you go there, are you festive now because it's the Fiesta bar? No. That's a disappointment. I think if you're going to have something called the Fiesta bar, it should be festive. I understand you're not even allowed to go in there and choose anything yourself, that you still point at it and they still build the stuff for you. Is that true? It's like if you go get a potato, they still put the stuff on it. That takes away all the fun of the whole idea of a potato bar. All right. So I'm thinking it's about time we kind of mix this up a little bit, increase our knowledge base. Because what we're really going to want to do, and this is what I really want to talk to you about today, is I want to talk to you about what this is really about. This has never really been about resistors or capacitors. This has been about resistors and capacitors. That's what this is really about. I could spend the rest of the semester doing just, resistor circuits or capacitor circuits, but they're just boring. So what we want to talk about today are RC circuits. Now, I want to stop for just a minute. I need to hit pause on this. This is a circuit that isn't parallel or series. I mean, take a look at it. What would you combine together if you were trying to find the series or the parallel portion? If you look closely, you can't. I mean, if I didn't have this here, sure, it's just two parallel legs with some series in there. But the moment I add this in here, I am adding a potential pathway that allows for a potential difference at the midpoints of the two resistors. So none of these are in series or in parallel with each other. This can't be solved by piecewise reduction. The only way you can solve this is using Kirchhoff's laws, which, by the way, I want you to think about what Kirchhoff's laws would generate here. For just a moment, I want you to realize what Kirchhoff's laws would really be about if you were forced to use them. Right? In fact, we'd have all of those different voltages, and I don't know what any of them are. More importantly, it's not just that. I would have current 1, current 4, current 3, and current 2. And this is called the bridge resistor. That's why you see a B here, because this circuit is known as a Wheatstone bridge. It has a use. And now imagine all the possible loops we could generate, because we have to generate one loop that accomplishes each one of these resistors. So how about I could do the whole outside one? That's going to be V minus V2 minus V3 equals 0. And I can imagine a inner loop with V minus V1 minus V4 equals 0. I need at least one more, don't I? So how about this loop? That gets my other resistor, so I need to include it somehow. So this is V minus V1 minus VB minus V3 equals 0. There are more, but at least now I've accomplished each one of my resistors. But now I have junctions. I have to go to each junction. And I don't know what direction the currents actually are. I'm guessing. So I'm going to say I1 goes in and I4 and I bridge go out. I have more junctions. How about right here? I from the battery goes in. Better not use battery, so I'll just say I goes in. And then I1 and I2 come out. So I've generated so far 5 equations, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 unknowns. I better start generating some more equations. V equals IR is going to be next, right? To connect all these together. The only way to actually solve one of these problems, if you can't do piecewise reduction, is through Kirchhoff's laws. And Kirchhoff's laws generate one equation per loop and one equation per junction. And then Ohm's law generates another set of relationships for each circuit element. You realize what you're going to create is a massive system of linear equations, of which you are going to be doing an incredible amount of substitution in order to get yourself a solution. These are impossible for us to solve in a reasonable amount of time. I mean, yeah, you could solve this, but this is not a 15-minute problem. It's a 2-hour problem. There are shortcuts. That book I brought out to you, the whole first and second section of the book is about all the shortcuts around Kirchhoff's laws when you can't use piecewise reduction. Real circuits are complicated. The reason that this circuit has a usefulness is because it's called a Wheatstone bridge. The bridge resistor can be carefully measured for its resistance properties by tuning the bridge specifically for that resistor. It's one way of creating a tunable circuit that allows for precise measurement of resistance. Resistance can be hard to measure because trying to measure it affects the circuit. So when we talk about circuits, there's the circuits that don't fit the mold. The other thing that we're going to have to address is the fact that when we actually create circuits, even simple resistor circuits like this one, this circuit isn't as simple as it looks. It seems like it should be. But if I wanted to create a laboratory to measure this circuit, like say I wanted to measure the current, I'm not sure if you're aware of this, but to measure current, and don't think that this is not what this is about. I'm not just talking out my butt. This was the lesson for today, to talk about the difference between real and ideal circuits. We are now talking about their differences. If I wanted to measure the current in the circuit, I have to put a meter in line so I can see the current passing through the circuit. Measuring current requires that you're in line in your circuit. The problem is the only way I can actually do that is if this meter itself allows for current to pass through it, which means this meter probably has a small amount of resistance. But its resistance adds to the total resistance of the circuit. And because it adds to the total resistance of the circuit, it changes how much current's being produced by the battery. The mere presence of the meter affects the circuit, and there's no way to measure the current without affecting the circuit. And although there are other ways of measuring current, they all affect the circuit in the same way. What if I wanted to measure the voltage? Well, I could put a voltmeter here. What do you think the voltmeter is going to do? Although it wants to measure the electric potential, it's got to do so by probably drawing a small amount of current and using that small amount of current to measure that electric potential. Generally, the resistance of the meter is large when it's a voltmeter, so that it doesn't draw too much current, but its presence affects the resistance of the circuit, and therefore its presence affects the actual current produced by the battery. Ideal meters have either zero resistance or infinite resistance. Amp meters, zero resistance if they're ideal. Voltmeters, infinite resistance if they're ideal. There are no ideal meters. Of course, now you understand why our voltmeters have different places for you to put the wires, right? You have to put it on the one that has the small resistance for the current measurements. And you have to put it on the one that has the large resistance for the volt measurements, which is why there's a whole bunch of holes at the bottom of that voltmeter. This is why. Now, the other thing to think about here too is that our circuits aren't this simple. Even though that all sounds simple, the wires have resistance. There's no way around that. And worse, our voltage supplies have resistance. A real battery is a combination of a potential difference and a resistance. Now, it's not like you crack open the battery, you're going to find resistors in it. The resistance of a battery is the limit of the battery to produce current. That's what the internal resistance of a battery is, the limit of a battery to produce current. So all of these are things that we have to study. And they've all been studied, of course, in AP Physics 1 to various degrees of success. If you've never studied these, I'll tell you the parts that you have to pay attention to. Internal resistance. There are whole entire FRQs dedicated to internal resistance discussions. Qualitative descriptions of the difference between ideal and real measuring devices. You should be able to describe why there's a difference between real and ideal measuring devices. And you should understand that voltmeters have very large resistances so they don't draw much current. And amp meters have very small resistances so they don't have much of a potential difference across them. All things that we try to do to minimize our impact on actually measuring what's happening in the circuit. Now, it would be inappropriate for me not to at least spend a few seconds talking about internal resistance and why internal resistance is what it is. To understand internal resistance as a limiting factor, here's what I want you to do. We have 6-volt batteries in the back, and they have a very low internal resistance of approximately 1 ohm. It's actually lower than that on the new ones. You've used the 6-volt batteries, and you guys probably can attest to the fact that they hardly ever actually measure 6 volts. They always measure something less than that. Even when all you do is you put the voltmeter directly on it. Still, they don't hardly ever measure 6 volts. So here's what I want you to do to show you why this is true. I want you to determine the voltage across this resistor for 5 circumstances. For this resistor, we're going to start with a resistance of 1,000 ohms, then 100 ohms, then 10 ohms, then 5 ohms, then 1 ohm. So we're going to replace this resistor 4 times. Each time, what I would like you to do is determine what the voltage is across that resistor in this ideal circumstance. I'll do the first one. In the first circumstance, I'm going to put a 1,000 ohm resistor in series with my 1 ohm resistor, the internal resistance of the battery. And I'm going to try and determine what the voltage that I would measure across the resistor is. It's not hard to do. My reduced circuit will have a total resistance of 1,001 ohms with a 6-volt source. This will tell me the current. Now, if I want to figure out what the voltage is across that resistor, the voltage is going to be the current, 6 over 1,001 times 1,000. And you'll notice I get a value slightly less than 6, right? 5.999 something. So what I'd like you to do is repeat that now for a 100 ohm resistor, a 10 ohm resistor, a 5 ohm resistor, and a 1 ohm resistor, and you will understand what I mean by saying the internal resistance is a limiting factor. You guys about done? This only takes like a second. Once you realize what you have to do. I mean, this one's what, 3 volts? And just 5 volts? 10/11 though, I can't do that in my head. So what's the next one? 5 point what? 5.4. All right. And the 100 one's got to be 5.8 or 5.9. Internal resistance. What it really means is that your battery can't provide infinite current. It can't. So as you try to draw more current out of the battery runs into a limiting factor. And that factor is interpreted as a resistance. In fact, the lab we're going to do later this week, the first one we do is an internal resistance lab, where we have to measure the internal resistance of the battery. In fact, if you want to impress me, and I would be duly impressed, could you come up with a way of measuring the internal resistance using actual resistors in the battery? I want you to think about this for just a minute. We don't know what the battery's actual internal voltage is. We just know what it's rated for. All we can do is measure the output voltage when we connect things. But we really don't know this or this. Say we can assume that this is true, that if the battery says it's 6 volts, internally the acid is creating a 6-volt potential difference. What data could we collect to measure this? I think this is a challenging question. And if you're good at this, if you are good at doing all this piecewise reduction stuff, then this is on the right level for you to think about. How would we do a lab where we measured this internal resistance? I will tell you that for a battery, it is a constant. Okay, that's it for today. Tomorrow, fun stuff. RC circuits. I'm so excited. But for today, that's all there is. You guys at home have a wonderful day. I'll see most all of you later at some point or another. See ya.